Thank you, Bill, and thank you to the organizers for inviting me to talk about asymptomatic reservoirs. I think anyone who has been doing community surveys in endemic settings in Africa will recognize the figure that the vast majority of infections that you see are asymptomatic, or at least they don't have fever. And once you look by qPCR or by nested PCR, you roughly double the number of infections that you see. And we like to call that asymptomatic. And I think there's more and more evidence that there are actually individual consequences of these asymptomatic infections, at least if you talk about microscopy positive asymptomatic infections. So also in our studies in Burkina Faso, we see very clear indications of low-grade hemolysis, inflammation. There are clear indications for salmonella associated with asymptomatic malaria, and there's also indications that school performance is worse in children who have a chronic infection. So I think this term asymptomatic malaria is problematic, and I think it is actually a really good discussion to have under what circumstances can you actually monitor infections and not treat them, because the evidence is building up that actually, at least for microscopy positive infections, there are negative consequences for the individual. I still believe that there are many very important questions that surround asymptomatic infections that mean that if you have well-designed studies, you should follow them longitudinally and see what happens to the individual, but also to their public health relevance. And I will talk about the public health relevance. So are they transmissible, and in what sense are they important for sustaining transmission? Problem was, I was here 2 years ago, and I talked a lot about this topic, and I wanted to avoid any slide that I used before. So now I'm actually going to do what Elizabeth also said. We should share the data. I'm only going to present unpublished data on some things that I think are relevant for this topic. So first I'll talk about controlled human malaria infections in Nijmegen in the Netherlands, where we managed to induce gametocytes. It's quite a useful tool to look at when do people become first infectious, and potentially also a useful tool to evaluate interventions. Then I'm going to address, first time presented, well, perhaps it will be very disappointing, but assessing infectivity by skin feeding or membrane feeding. Does it matter how you do that? And then lastly, I will talk about the topic that is actually most relevant probably for today, the contribution of asymptomatic infections to the infectious reservoir during intensive malaria control. So that really touches on some of the topics raised earlier by Kim and also Larry. So one thing that I think is really nice, and I also saw some really nice posters on this topic, poster 23 and 28, I recommend for over lunch, that we no longer have to rely on microscopy, we no longer have to rely on PCR to measure total parasite density, but it's actually an expanding toolbox of markers that will tell you what's happening during an infection. So we now have a very sensitive ring stage marker, SPP1. You can look at sexually committed ring stage parasites. AP2G is a master regulator of gametocyte formation, so you may see which parasites are destined to become gametocytes. And then we can look at mature male and mature female gametocytes. And all of these assays actually have a detection limit at or below 1 parasite per microliter in a standard, say, 50 to 100 microliter finger prick blood sample. So I think these are very useful tools. And I will illustrate the tools with controlled human malaria infections. In Nijmegen, we don't have malaria since the 1970s, so we have to give it to people. And we've given people Plasmodium burgii infections last year, which was novel, but we also managed to induce gametocytes. And we've so far done 40 volunteers. We gave them either mosquito inoculation, so sporozoites, mosquitoes on the skin, infect volunteers with Plasmodium falciparum, or blood stage inoculation. We give them a low treatment of piperaquine, that's half the dose that's in DHA piperaquine, only a single day, to attenuate the infections and not boost gametocyte production, but just allow gametocytes to form. And that allows you to look at when do gametocytes first arise and when are people first infectious. So we see a very nice predictable pattern. Here you see in black parasites, asexual parasites, in red female gametocytes, in blue male gametocytes, and they really appear after 8.5 to 12 days after the first peak of asexual parasites, which is an indication that actually from the first parasites in the bloodstream. Some of them commit to become gametocytes. So this is 3D7 parasites by mosquito stage inoculum. This is 3D7 parasites by blood stage inoculum. And the asexual parasite densities are actually very similar, but we achieve much higher gametocyte densities, about 10-fold higher, which is intriguing. And I think it's useful because it also allowed us to test whether AP2G transcripts are actually predictive of this variation in gametocyte production. And these are all very low parasite densities. So we treat our volunteers at 5 parasites per microliter, examined twice daily by qPCR. And still with these very low densities, you see a very strong association between AP2G transcripts and the number of gametocytes that appear 12 days later. So I think this is the first time that's been shown. And I think I'm looking forward to actually using this in the field because I think it could be a very useful tool. The other thing that's great that the majority of these blood stage inoculated volunteers actually became infectious to mosquitoes after about 21 days after their inoculation. And we're trying to also set up this model in African settings where, of course, the immunity is very different. And this could be a very useful model to evaluate transmission blocking interventions. And we need something to rapidly say this is not going to work, so you can focus on the interventions that may work. So this is something we hope to do in the coming few years. So we have done membrane feeding. Here you see blood in a feeder, and there you see my arm actually against the cage of mosquitoes. And by membrane feeding, we managed to see infections in 7 out of 12 volunteers. By skin feeding, 9 out of 12 volunteers. And actually the mosquito infection, the oocyst numbers, so the parasite numbers in mosquitoes were also higher by skin feeding. And this is not novel. It's in line with literature, and together with Tom Churcher, some years ago we did a meta-analysis of a few hundred of these experiments. And it's very clear that you have more infected mosquitoes by skin feeding. So this could be very exciting. If parasites are clever, they're in the skin. Trypanosomiasis, there's great examples, but also in the intra-erythrocytic parasite Babesia, there's indications that they're present at higher concentrations in capillary blood rather than venous blood. It could also be utterly boring because the left graph, I mean, that's blood in an anticoagulant. It may activate. It could also be a technical element. So I think this is a long-standing hypothesis, and it made sense to actually test it. So we've done 2 studies in Burkina Faso in adult gametocyte carriers, so microscopy-positive gametocyte carriers. The first one, we took heparin blood samples, offered it to mosquitoes, and then 7 days later, you can see these beautiful oocysts, or not, on the mosquito midgut, and we examined a good number of mosquitoes per individual, and we also did skin feeding. And then the nice thing we did, I think, is that we gave a second blood meal in EDTA, and we gave that to mosquitoes. And we sacrificed those immediately, or after exactly 15 minutes, we ruptured the mosquito and released the blood in RNA Protect. And we had pools of mosquitoes. We had 16 mosquitoes sacrificed immediately after membrane feeding, 4 pools of 4, and 12 after skin feeding, 3 pools of 4. And we managed to quantify parasites in these blood meals. And then you can do an absolute quantification of gametocytes or the gametocyte fraction. So of all parasites, asexuals and gametocytes, what proportion is gametocyte? So this is an empty graph. There's nothing wrong with your eyes. On the x-axis is the log parasite density in the skin feed, on the y-axis in the membrane feed. If there is any sequestration, you would expect the dots that will appear any moment to be below the line. And actually, they're completely on top of the line. So ring stage parasites in green, male gametocytes in blue, female gametocytes in red. They're present in equal numbers in mosquitoes that fed on the skin and mosquitoes that fed on EDTA venous blood. So you can also look at gametocyte fraction, and here you see in the first black cloud of dots on the left is venous blood, and then gray next to it is mosquitoes that fed on venous blood, and then the same for capillary blood. And again, the fraction is the same, and if you plot the fraction in paired experiments, you see a very strong association. So I think this is an indication that in this population, it's a small population, there doesn't seem to be huge sequestration. There actually doesn't seem to be any sequestration in the skin. Well, before we did this study, we actually did a more ambitious study with Matt Marty in Glasgow and also with his team in Harvard, where we said, let's answer this once and for all, do minimally invasive skin biopsy samples, first in a small group of volunteers, adult gametocyte carriers again in Burkina Faso, and see if we can find gametocytes in the skin. And this was a study we did actually before the other study. The reason I'm not going to show a lot of results is actually, that's part of the result, we haven't found many gametocytes yet. So this is work that's still ongoing in Matt Marty's lab. We do have beautiful skin biopsy samples, so the quality is perfect. We just need to do the last immunohistochemistry assays. We have done, in my group, for part of the skin biopsy, the molecular assays. And I'm going to show you a busy graph where on the x-axis you have the gametocyte fraction in venous blood. So that goes from near 0 to 100%. Some only had gametocytes. On the y-axis you see in black dots in capillary blood, and in the gray symbols you see in the skin biopsy samples. So although there's a lot of noise, and you would expect that with tissue, again, the dots surround the line rather than show a very clear pattern. So probably there's not a very strong effect of gametocyte sequestration, which means that although membrane feeding is not the most sensitive tool, it's a useful tool. And also means that my career so far is largely built on membrane feeding is not completely useless. So it means that you can actually use membrane feeding because it's nice and scalable. You can examine many mosquitoes, and actually we are now also working on enrichment approaches where we have a foie gras membrane feeding where we concentrate a lot of gametocytes from large volumes of blood and then see if these gametocytes are infectious despite their low density. So you can really play with this for your questions. So it's plausible, but it gives these conflicting results. So in our studies, and we've done this in Kenya in 2 sites, and in Burkina Faso and in Ethiopia, we see that more than 90% of the mosquito infections seem to arise from the asymptomatic reservoir, which makes a lot of sense if you think about all the asymptomatic parasites that are out there. But then Steve Meshnik and Jessica Lin, they actually published from Cambodia that more than 95% of the mosquitoes are from clinical cases. So are we actually really do we have conflicting results, or are we measuring the same thing but at different time points on the path to elimination? And that's the last part of my talk, and I'm lucky that I'm working with one of the isomer studies in Uganda, where something extraordinary happened over the last few years, and you see this on the in the graph, where you see in the green line you see malaria incidence over the years. And this is, I can't see the dates, but you can see the malaria incidence in green and the parasite prevalence in red. And it used to be very high. This was a very high burden area with an entomologic inoculation rate above 300 bites, infected bites per person per year. And then LLINs were distributed, not too much happened. IRS with bendiocarp, severe reduction. IRS with actelic, even more of a reduction. And this has been sustained. So spraying is continuing, and actually this area went from a very high endemic area to a very low endemic area, surrounded by a lot of high endemic malaria. So it's not an elimination setting, but it's a great area to actually say control is phenomenal here, very efficacious. What happens to the infectious reservoir? So within the PRISM cohort with Grant Dorsey, Brian Greenhouse, and John Reck, and many great people in Uganda, we are following 476 participants, adults, but also, or mostly children, but also adults. Every 4 weeks, sampling immediately processed by qPCR with a sensitivity around 0.1 parasite per microliter. And then as soon as someone is positive, we select them for membrane feeding. And here you see, without any feeding results, you can already see why this is so interesting. So on the top, you see the start of the cohort. Parasite prevalence was 19% by qPCR. Parasite density, that's the distribution in gray, and the gray distribution is on all the 3 graphs. 30%, about a third, is above 100 parasites per microliter. Now, a few months later, parasite prevalence declined to 13%, to 14%, and only 13% is above 100 parasites per microliter. And you see, actually, if I can use the analogy, the iceberg is sinking, parasite densities are declining. And the last survey this year, only 6% parasite prevalence by highly sensitive PCR, only 7% of those positives have more than 100 parasites per microliter. So this is a really interesting scenario, what happens to the infectious reservoir. And we've done 300 membrane feeding experiments so far, only 10 on clinical cases from the cohort, but because we're interested in clinical cases, we recruited more clinical cases from a neighboring area that doesn't have IRS. And this is our insectary container, or two containers, two shipping containers, not sea containers, I was told yesterday, shipping containers that were built into an insectary. And the likelihood that you infect mosquitoes in the bars increases with parasite density. That's no surprise. What's interesting that some of the individuals with 10 parasites, up to 10 parasites in total per microliter, they still infect mosquitoes. And you see on the right graph, you see the proportion of infected mosquitoes. So it goes up to 80%, but for many it's very low. That one person where my PhD candidate said, we have to remove this person from the graph. I said, no, we have to keep it in. Because this was clearly an extraction failure. This person actually had gametocytes on the slide, the bar on the left, but was PCR negative. So this is clearly a parasite positive individual. In this context, so parasite density is declining. We do sometimes see incident infections that are asymptomatic, and they can go to quite high density. So these are individuals who still have a good level of immunity, but mostly you see parasites declining infections declining in parasite density. So the clinical cases actually here, they're not very infectious. So the parasite densities are quite high. If we combine all clinical cases, about 3,500 parasites per microliter. Within the cohort, much higher. These are real clinical cases. Within the cohort, also 90% measured fever prevalence in clinical cases. They don't infect many mosquitoes. So we still have to do the gametocyte data. So that's coming, but it's clear that here the clinical cases are not extremely infectious. So this is what, if you take all the 338 infected mosquitoes, where did they get their infection from? More than half from the highest parasite carriers, so 1,000 parasites per microliter or more, but 15% from parasite carriers with less than 100 parasites per microliter estimated by qPCR. So these could be called submicroscopic infections, at least difficult to detect with IDTs or microscopy. Now, the thing is, and I think that is unique about this cohort, that parasite prevalence and density declined so much during that period. And we have this continuous monitoring every 4 weeks. We do membrane feeds to see how likely is it that an asymptomatic case infects mosquitoes. And the densities decline. So what you would expect, you also see that this is 2018, 2019, the different months. If I pool the experiments, that there was a moment that more than 25% of all the asymptomatic parasite carriers infected at least one mosquito, and now we're much lower. So these are all parasite positive individuals, but the likelihood that they infect actually declines, just as a function of their parasite density. So perhaps we are approaching a Cambodia situation with huge differences. I mean, this is still a population that has immunity, has seen a lot of malaria. We're approaching a situation where asymptomatic seem to become less and less infectious. And perhaps at some point, these parasite densities are so low that they're still there. You can measure them, but unless they rise, and we don't see that, they mostly just go down, they start to become irrelevant. You may ignore them, but of course the big question is, when can you start ignoring them? And obviously you don't want to do that too early. So this was everything I presented is work in progress. So we're also assessing mosquito exposure, which of course is a very important part of the equation. Now we're artificially examining mosquitoes as if every person was bitten by 70 mosquitoes that all survived up to day 7. That's not the case in Nagongera in Uganda at the moment, so we're doing that at the moment. So some concluding remarks. So in malaria-naive individual, gametocyte kinetics are predictable, and you have an immediate production of male and female gametocytes, and within 21 days after the first parasites are inoculated, either by mosquito or by blood stains, you see infectiousness. Direct skin feeding results in higher mosquito infection rates compared to membrane feeding, but it's probably not due to gamete site sequestration in the skin. And in many African settings, asymptomatic infections are responsible for the bulk of infections to mosquitoes, but their importance may actually decline when highly efficacious control is sustained for many years. And with that, I would like to have a fairly incomplete slide of the many people involved and the funders, European Research Council and the Bill and Melinda Gates Foundation. Thank you very much.
Fantastic. Thank you, Teun. Other questions? Yes, Kim.
Thanks, Teun, for the really wonderful presentation and a huge body of work that's very helpful. I had a question. You stopped at the point of saying whether a mosquito was infected or not, but have you looked at the density of infections within the mosquitoes and then the density of sporozoites in the salivary gland to see if there is, if reduced density in the human of gametocytes in the humans ends up resulting in reduced density of sporozoites in the inoculation?
That's a very good question. And I know what meeting that came from. It's something that we are now doing in the second phase of this study. So I think there is a health hazard also in these. In some of the insectaries, you can't keep mosquitoes until they're sporozoite positive. So now we've installed an incubator in the insectary so we can actually keep mosquitoes until they're infectious and until they have sporozoites, and that's in the next phase we actually want to do that. Because I think it's an uncertainty. At the same time, we were just discussing the estimates of number of sporozoites per oocyst. Scenario says 9,000 sporozoites per oocyst. Flaminia and I said it's probably a bit lower, but the number of sporozoites that reach the salivary glands per oocyst is probably in the range of 1,000, 2,000. So whether that's enough to render a female anopheline infectious for the rest of her life is a question. It's an important question. I think all the evidence so far suggests probably they are, but I think it's crucial to examine, and it will come.
Toby Lehman, NIH. I would like to first congratulate you for a great work. I was wondering if you could talk about how long people remain infected and infectious if they are not exposed to new mosquito bite, new infectious mosquito bites. How long is this infectivity period? And also, if you could comment about recrudescence and the relationship between exposure to uninfected mosquitoes for recrudescent events as a potential stimulus.
This is everything I want to do in the next few years. The first, my memories, I woke up at 3 a.m. I immediately forgot the first question, which I can answer. Oh, how long infections? Very good. Yeah, so the unique thing is we now have, for some of these individuals, we have, I think, for one person, we have 14 membrane feeding experiments done over as many months. And some people are continuously infectious at low grades. Not continuously, but like every other month they're infecting mosquitoes. We had one person beautifully monitored who had an incident infection, and then we did 4 membrane feeds on this person, and then the person cleared the infection naturally, was infectious and highly infectious during those 3 months. So it's very variable, and it's something we're also doing with some detailed genotyping with Brian, the Greenhouse group, to look at whether these are really the same infections and what infections do you see in the gamete site fraction. So we enrich for gamete sites and also try to genotype that, and then also genotype the mosquitoes. So the next question about the mosquito exposure is extremely interesting. So we have submitted a project to the ethics committee, but in the end we couldn't fund it to actually look at chronic infections and then expose them to mosquito bites and see whether that's a stimulus for gamete site production. There's some indications for that. I think it's interesting. I don't know how important it is at a population level, but I think it's something that I'd love to do.
Tamaki Kobayashi from Johns Hopkins University. I have a question about multiplicity of infection. As the parasite density went down, did it have any effect on the actual multiplicity of infection at all?
That's another good question. It's something we will look into. We have done one very puzzling, the outcomes were very puzzling with Dimeworth and others, to look at the number of genotypes you detect in mosquitoes and the number of genotypes you detect in the blood meal. That was the source for those mosquitoes. And we consistently found many more clones actually in mosquitoes than in the humans. So it could be, I'm sure it's a technical thing. So the fact that you have your minority clone is difficult to detect in blood, but your oocyst formation is a PCR in itself because you multiply your copies extensively, so it's easier to pick them up. Whether it's important to actually assess, to determine how many mosquitoes become infected is, I don't know. It also has to do with mosquito immunity in some ways. So I think that's an excellent question.
Hi, I'm Matt Ippolito, also from Johns Hopkins. My question is whether you think that this observation of an increase among clinical cases and their contribution to the infectious reservoir in low endemic areas might explain why we see drug resistance first arise and propagate in low endemic regions, the logic being that these are drug-exposed individuals.
Yeah, it's interesting hypothesis. I know of someone who has really interesting data on this, but I'm happy to talk about my own unpublished data, but not someone else's, but about how parasites may respond to their environment and whether artemisinin-resistant parasites are more prone to form gametocytes. So I think that is something that is coming and would be very exciting, but I'm not allowed to talk about it. I was not involved, unfortunately, also. Thank you very much.